Our project started with a broad problem. Human CO2 emissions are threatening public health. CO2 is a direct pollutant in ways such as directly impacting the acidification of our oceans. It is classified as a greenhouse gas, meaning we need CO2, but too much of it in our atmosphere increases the absorption rate of radiative energy from the sun. Transportation alone accounts for 28% of the United States CO2 emissions. The carbon emissions comes from the hydrocarbon fuels, such as gasoline, diesel, propane, natural gas, and others, being burned to convert their chemical potential energy into useful kinetic energy. While batteries and electrics provide one solution, energy density and speed of refueling are favorable with internal combustion engines. We focused on a way to reduce CO2 emissions while still utilizing internal combustion engines because our society is built around internal combustion engines. A potential candidate for replacing hydrocarbons as the fuel for combustion engines is ammonia. A molecule of ammonia is composed of one nitrogen atom and three hydrogen atoms, producing nitrogen gas and water upon combustion. Neither product of combustion is harmful to our environment, and the ammonia itself can be produced through green, renewable energy processes.
Using a small engine from a snowblower, we aim to modify it to run the engine off of ammonia. However, switching to ammonia presents additional challenges. As a gaseous fuel, metering the air-fuel mixture is not as simple as using a classic carburetor-style design. Also, ammonia takes more energy input to reach combustion. Most importantly, ammonia has been classified as a Class 3 hazard to health by the National Fire Protection Association. Because of the health risks, we needed to minimize any leaks of ammonia that could occur and hold safety as our highest priority. Before we get into our final design, we need a basic understanding of how a 4-stroke internal combustion engine works. During the first term of this project, while we were taking apart and cleaning the engines, we decided to test one of the spark plugs of the engine. Let's walk through the 4 strokes that make up the Otto cycle. This is the start of the intake stroke. The intake valve is opened, the piston lowers and pulls the air-fuel mixture into the combustion chamber. This is the start of the compression stroke, where the piston rises in the cylinder and compresses the air-fuel mixture. This is the start of the power stroke. You can see the spark igniting the air-fuel mixture and forcing the piston downward. The last stroke is the exhaust stroke. The exhaust valve is opened and the piston moves up the cylinder and the exhaust gases are expelled.
The Roots-type blower is controlled by the crankshaft, which consistently rotates the lobes of the supercharger for both the air and ammonia at the same speed.
Here we are zooming in on the ammonia side of our supercharger to take a closer look. The ammonia from the storage tank enters the pump from the bottom and is pushed along the outer edges of the pump and squeezed out through the top. The gears ensure that each of the lobes is spinning at the exact same speed. A timing belt pulley system connects the turning crankshaft to the supercharger, providing the supercharger with the rotational energy that it needs to operate. The plumbing system, seen here, connects the air and fuel output from the supercharger into the intake of the engine. The reservoir serves as a buffer to prevent large pressure spikes between each of the intake strokes, because only one intake stroke occurs per every 2 revolutions of the crankshaft.
Due to COVID-19 complications, our team was not able to finish manufacturing the supercharger and run physical tests planned for D-term. Our design and ammonia-powered internal combustion engines as a collective shows promise for future work, and we have left off this project at a place where we are confident will be easily picked up and carried through to fruition.